my capacitance I can put in terms of that geometry stuff. So that's what we're going to do. So the energy in the capacitor looks like this. Okay, so we got a half. Capacitance, epsilon naught A over D. Voltage here is electric field multiplied by the distance. Okay? Electric field is sigma over epsilon naught. Multiplied by the distance d. Okay? So now I'm going to square this like this. Okay, so let me write this stuff out now. So I get 1/2 epsilon naught A over D. Since I want this stuff in terms of the electric field, I'm actually going to keep the E here. That E then becomes squared, and I get a D squared here. Which means the total energy stored inside of this thing is 1/2 epsilon naught E squared A D. Oh. Well, that doesn't look like anything I can use in general. The E squared is fine because I'm looking for energy in terms of electric field. The epsilon naught is fine, right? Because that's just a constant. Half is fine, half is half. No matter where you are, that will translate into something universal. What doesn't translate is this A and this D. Because the A and the D are specific to the capacitor. We have failed, almost. We can't talk about the energy of an electric field just in terms of the energy, because it would depend on how much electric field you have. In other words, if I've got electric field here, right, it has so much energy, but if I've got, of course, more electric field in other places, I'm going to have more energy. So instead of an energy, what we do is take a look at this right here. What is this in terms of that capacitor? Yeah, somebody said the V word. What is it?
Volume.
Volume. That's the volume of the capacitor. You've got the area of the plates multiplied by the distance. It's a little tricky, but that's what it is. That's the volume. So instead what we can do is we can define a U energy density. So little u is defined as being energy per volume. Energy per volume. And when we do that, the energy per volume is 1/2 epsilon naught E squared. And that's our energy density. Energy per volume.
So we just ignore the AD.
Well, we've divided it out. So in other words, the term we define is the energy per volume. So it's an energy density. If I want to define it, it's joules per meter cubed. That would be the standard units here. Because, of course, the more area or the more volume in which that electric field is, the more energy I'm going to have to make it. It takes a lot more energy to make a meter cubed of electric field than it does to make a centimeter cubed of electric field. Lots. If I had to get giant plates. So what we can do is we can put this in terms of the energy here, that's a microscopic form, or, of course, the macroscopic form is just the energy stored on a particular capacitor.
Professor?
Yes?
Capacitors' energy increases with their surface area, but decreases with the distance apart. So could you have the same volume representing a different?
Oh yeah, if I put more charge on this thing, if I put more charge on it, let's say, right, then I increase the electric field. So there's a larger energy density. Multiplied by the same volume, you get more total energy.
Let me rephrase it, I'm sorry. You could have two different capacitors that have the same volume, but they have a different storage capacity. Is that correct? Because one could have large plates and a short.
Oh yeah.
Okay.
But anytime you put the charge on it, it's going to have a different voltage and a different capacity. See? Yes.
Okay.
All right, now, let's see. Is there a good picture of this? Okay, good. They got it. There's a good picture. Now, so far we've been working with air, or we've been working with what we call vacuum. Okay? That's pretty impractical. Because in order to create these little tiny little capacitors, right, and separate them with a vacuum gap, you know, it's kind of hard because then you have to make sure that nobody kind of accidentally punches this in and go connect the two sides, and you don't have a capacitor anymore. So almost all capacitors have something in the middle, something in between the capacitors. So something in between the plates to hold the plate, at least to hold the plates in place. Okay? Now, there are things that we can put in between the plates called dielectrics. So if I have the two plates of capacitor, what I do is I put a dielectric in here. And what that dielectric will do is that dielectric will increase your capacitance, increase the capacitance. Now, how it does it is because it's made of some type of polar molecule. So what happens inside the dielectric much better than anything I could draw, okay? What happens is because it's made of some type of polar molecule, what happens is that the electric field goes this way, from the plus side of your plate to the minus side of the plate, okay? Now, with the vacuum, you just have the positive charges here and the negative charges here. When you put a polarizable material in between them, though, that polarizable material is going to put its negative side toward the plus side of this plate here. And its positive side is going to be with the negative side of the plate over here. And what this essentially does is, now all of a sudden, the electric field has been reduced in between them. So there's less voltage. So essentially what it does is I can store the same amount of charge on those plates, but use less voltage. If I were to keep the voltage the same, what would happen is, then I could put more charges on this plate to cancel out the charges from the dielectric. The charges from the dielectric are fixed to the dielectric. It's not a conductor, but it's polarizable. So what it essentially does is it has charges over here that help cancel out the electric field so that you could put more charges on the capacitor itself. And that's how it increases the capacitance, because it lets you put more charges on the capacitor itself. This diagram is on page 799 of the book, so that way reference it, because like I said, I can't do by drawing would stink. So this is much better graphics. Easier to explain off of it too. So now the dielectric constant, it depends on the material put in, is this kappa. Your textbook is very bad because they make their kappas look like Ks. It's not really a K, it's supposed to be a kappa. Oh, yes, because I zoomed in. That's one good. There it is. See giant K? Okay, there we go. All right, so the giant K, that's a dielectric. And it depends on what you put in, okay? So when they talk about vacuum, the vacuum, which is perfectly, which is outer space, so to speak, 1, okay? Okay. If you have air is 1.0000059, and that's generally why if we say air, I say air on a test, unless I tell you specifically, 1, okay? Air or vacuum is pretty much interchangeable because air's not really that polarizable. It's not really going to help you. It's just air. But there are some things that you can put in that would help rather significantly, and let's see if I can find some good ones. Teflon. Teflon, that's interesting. Teflon is 2.1. Mylar, 3.1. Plexiglass. There we go. Douglas. Plexiglass only has 1. Oh, that's cute. That's cute. I love this. I'll show it to you. Look at the word plexiglass that they have here. That is in there. That's a hand. Yes, it's trademarked. That's why it's spelled with just 1 S. It's trademarked spelling. So, see, I spelled it wrong. I'm sorry, I can't write this down. Yeah, I don't want to have any copyright infringement. So it's 3.4, and basically you'd look these things up in the table. Here's an interesting one. Water is 80. Well, good luck kind of getting it to stay in the middle, and it would have to be like pure water, because you wouldn't want any impurities in it, because if I put salt in water, it becomes a conductor. It's not an insulator. Pure water is a polarizable insulator, so it has to be pure. So that's a bit of, I don't think they really use this, but it's there. If you happen to have it in a pure water bath with no, it's
the more polarizable the material is, the higher your.
Yeah. And water's it's water and liquid water, of course, the molecules can move easily to be polarizable. But it has to be pure, or else. If you were standing in pure water and you threw, whatever high voltage wire in, you'd be fine. Of course, how much water around here is pure? We're in LA. It's definitely not pure. All right. So what happens is that the capacitance is equal to kappa multiplied by the original capacitance. In other words, it increases the capacitance by a factor of this kappa. And so what we do is I'm actually going to change the formula for a parallel plate capacitor to be kappa epsilon naught A over D, like that. And so if you're dealing with a parallel plate capacitor that's a vacuum, you just, kappa is just 1. Kappa is just 1. Okay. One thing that I need to let you guys know is that to be careful when you're just looking at this formula. Do not get the Greek letter kappa here mixed up with K. The kappa, the materials that you use for your thing have dielectric constants of 2, 4, 20, something like that, maybe. If you put K in, K is 9 times 10 to the 9. Okay? In here, I shouldn't have to do that much warning. You know, I teach it, but I teach 100V as well, so just want to make sure, you know, just cover all bases, you know. Then I have to, I get that all the time. Whee! Mega farad capacitor. Wow! Nobel Prize! Well, I won't announce it till next year after the gravity wave people get their Nobel Prize for this year. By the way, that was a really cool discovery.
It was.
Yeah.
That is something we've been waiting for
1.3 billion years.
well, yeah, that's pretty much how. So, also, the energy density, though, we have to rewrite that too, inside of a capacitor with the dielectric in it. Because what happens is that the energy is still the same. Just because I stick a capacitor, stick a dielectric in there, their total energy is going to be the same. The only reason why the electric field is less is because I've moved these other charges there. So in order to account for that, my energy density formula changes to, and I'm going to write it like this, 1/2 kappa epsilon naught E squared. Now there is a shortcut to this, a slight shortcut. Instead of saying epsilon naught, you could also call this epsilon, which is basically kappa multiplied by epsilon naught. And then kappa, this epsilon, would be the electric permittivity of whatever. Electric permittivity of anything would be defined as my epsilon naught. Notice that when I have the dielectric here, the electric permittivity increases because what I can do is I can put more electric field for the same charges I put on the outside. In other words, I can get more charge. And then, of course, the epsilon naught would be what we call the permittivity of free space, which is a vacuum, which is when K equals 1. Now you know why I said epsilon naught is the permittivity of free space. Because that is vacuum, you put the kappa in there, you get that. I'm going to go ahead and treat the two constants separately in these formulas. Okay? So that way you don't have to go back and memorize it, just that epsilon is equal to kappa. Just remember, in the presence of a dielectric, these formulas change. Gauss's law of dielectrics? No. I'm not going over Gauss's law of dielectrics. Basically, Gauss's law of dielectrics, you just replace epsilon naught with epsilon in Gauss's law. That's it. There. That's it. Wow, I can do some examples. I got some time. All right, let's take a look at the, this ought to be fun. All right, let's make a parallel plate capacitor here. Okay, area of my plates is going to be 10 times 10 to the negative 6 meters squared. Zoom out. Zoom out. Zoom out. Okay. My distance D between the plates is going to be 1 micrometer. And now I'm going to fill the I like the 100, with the 100 version of this better. They give you paper. They give you the dielectric constant paper, things like that. So what I'm going to do is I'm going to fill this part of it. This part I'm going to have Teflon here. So this is Teflon. I'm just going to call that Kappa 1. So if I look up Kappa 1, Kappa 1 is my Teflon, it's 2.1. By the way, this situation is totally hypothetical. I can't imagine them doing this with a capacitor.
It's always pure material.
It's generally, I mean, why would you do this, unless you're teaching physics and you have a physics problem that you're throwing it, and you want your students to understand what's going on here. So up here, Kappa 2, I'm going to make neoprene. Neoprene has a kappa of 6.71. And then, well, that's interesting. Okay, so then at the bottom here, this bottom half here, I'm going to have kappa 3. Kappa 3 is going to be germanium. Germanium has a dielectric constant of 16. Dielectric constant of 16. Now we want to know what to do with this. What's the capacitance of this capacitor? Well, you start out, you think, well, epsilon naught A, kappa epsilon naught A over D, right? Which kappa do I use?
All three.
Weight then.
One.
But the
K2
percentage
would
of
And then
the
half of 2 and then half.
And K2 would have a weight of
A fourth, and
Fourth.
K3 would have a weight of
a fourth again.
a fourth. Okay, so you want to try a weighted average here?
Mhm.
Okay, so let's try a weighted average. We'll see if this works. Then I'll show you another way to deal with it.
Pull out a new piece of paper.
Yeah. Notice I have a new piece of paper
Yeah,
just to
okay.
do a weighted average.
Okay.
Okay, so the weighted average is, we're going to say our kappa overall is a weighted average of the kappas. By the way, it might work. I don't know.
Yeah, sure.
No, I really don't.
Give me a normal person.
I don't think I thought about it. I thought about it before, but then I wondered, what's that gonna? See what I mean? Is that? But we'll see. So anyway, we're gonna try a weighted average of these kappas. So that means we use an overall kappa, which is a weighted average of the other kappas. So we got half. We want half of this one, plus a fourth of this one, plus a fourth of that one, K3. Okay? So let's find out if this works. So kappa, I'll call it effective. How about that? The effective kappa to put in here, a weighted average of the other kappas. John, are you in here? John. Not here. Wait, John, are you here? No? No, John. He might be sick. That's our PLF. I was going to ask him if he ever tried this. See if I've honestly never tried this before. It might work. If it does, then hey, you.
Do you have the final answer for K?
What is this?
I believe it should be 6.7.
6.7. Give me another digit.
5.
4.
Okay.
Yeah, 5, yeah.
Okay, 6.75. Okay? So then what we'd do is we'd say that the capacitance is equal to kappa epsilon naught A over D. Okay? Kappa is 6.75. Epsilon naught is, actually let's just leave this in terms of epsilon naught A and D, okay? There we go. I could solve for it, but I want to leave all this in terms of epsilon naught A and D. Because I don't like the 8.85 blah, blah, blah times the negative. Is that okay? All right, now here's how I'm going to treat it. And we'll see if I get the 6.75. Right? What I'm going to say is this. If I put a thin metal plate right here, very, very thin metal plate right here, I do not change the physics of this thing at all.
The series.
But what I have is I've now created a capacitor here in series with these two capacitors in parallel. And the equivalent capacitance of those three capacitors should be the overall of what's going on inside of here. Neat, huh? So let's see if that works. Let's see if that works. Okay, so I'm going to make a C1. So C1 is equal to kappa 1 epsilon naught A1 over D1. A1 over D1. Okay? So kappa is 2.1. Epsilon naught, I'm going to leave it epsilon naught. A1, the area of the whole plate is A. So what about A1? No, area is the area of that plate. So the area there is the
Same area.
same. So that area is the same. So this is just A. How about the distance?
Half.
That distance is half. Divided by D over 2. And so what I get for my C1 is 4.2 epsilon naught A over D. That's one of them. Okay, that's one. Now let's do the next one, which would be C2. C2 is equal to kappa 2 epsilon naught A2 over D2. Kappa 2 is my 6.79. Epsilon naught is epsilon naught. A2, how about the area of that second one? It's half. What about the distance? It's also half. So then this is just this, that those things cancel out. So 6.79 epsilon naught A over D. Third one. This is when you should color code your notes, okay? Because I got nice color coding here. All right, so I got C3 is equal to kappa 3 epsilon naught A3 over D3. What happens here is very similar to what happens up here. The area is half and the distance is half as well. So what I get is I get 16 epsilon naught A over D. Now let's figure this out. Okay, these two are in what?
Series.
Parallel. Those two are in parallel. The capacitance here are going to do what? It's going to add. It's going to add. So since I want to add this, so I add these two together, I get this. So let's see, if I add the two together, I get, so C23 here is 2.79 epsilon naught A over D. Okay, now I want to do the series with C1. So I get 1 over C total, that's what we're looking for, is equal to 1 over 4.2 plus 1 over 22.79 in units of epsilon naught A over D's. Because there's an epsilon naught A over D in all the terms, it's going to be any answer. So I just have to manipulate the numbers. Convince yourself algebraically of that at your leisure for your betterment. All right, so what happens here, what I get?
get 3.55.
3.55. So the question is, did it work? No.
So the question is why?
Because if you think about it, what has to happen here is that these have to cancel out the charges on their respective plates. Well, I get have a couple of nice dielectrics over here. So this plate is going to say, hey, I can cancel out lots of charge. But that's not going to do any good if the left plate can't. So the left plate can't cancel out as much charge, and so we're kind of hampered by what's going on over here. And that's what turns out, because notice that this is counted in series with these two things being in parallel with each other. So in other words, you're kind of stuck with your least kappa, especially when something is touching the plates. It's touching the plate. Yes.
K2 and K3 are, if you look up, so like, they have like 2 here and then 1 down.
Oh,
How did you look at it?
yeah, you could do it this way if you wanted. You mean like this?
Would this be the same?
No,
Yes.
it wouldn't, because now you're treating these three capacitors different. Because now you get help from these on both sides here. You get help from these better ones on both sides here. And then that one, it'll do what it wants with its half, but at least you get some better on this side, both sides here. Yes?
So you have to treat K2 and K3 as series
And
and
then
then
put
K1
that in parallel with
parallel
K1.
them.
Mm-hmm. Okay, well, since I do want to get to more difficult stuff at some point, I'm actually going to take a moment and I'm actually going to start the next chapter. Okay? Because the third chapter that we do in here before your next test is a long one. So I want to make sure I can get through all the stuff that I need to get through for that. So I got a few extra minutes here. I'll go ahead and yes.
Can you put up the last page?
Oh, you mean this one?
Yeah, please. Yeah.
Or the one where I calculated
Yeah, the last one.
the last page how we treated those things. Yeah, there's a lot of, okay. There's a lot in the next chapters. Started. Somebody tell me when it's 20 till 11 if I don't look up. All right.
22.
No, it's not. Our pencil fine. All right, so now that we've finished talking about capacitors, or we're finished with that chapter, I'm going to start with what I'd rather started with in the first place, which is something more when we're talking about circuits, and that is current. So this is chapter 25. Okay, so far what we've been doing is we've been, anytime we dealt with a conductor, we basically say we stick an electric field in the conductor and the charges move and it stops. The charges move and they stop, and then we deal with that. Okay? But if the charges are able to keep moving, they'll never build up to build that counter-electric field. So in other words, when I first, in the last two chapters, when I put, if I had a rod here, right? And if I put an electric field in the rod, what would happen is the charges in that metal rod would move to the sides, create a counter-electric field to cancel out this electric field. But what if somehow they could keep moving? Well, then they would never build up. And the electric field would stay there. And they would keep moving. Okay? Now, exactly how they keep moving, well, we have to explain that in a bit. But the odd thing is their book starts out with this idea of putting an electric field in a rod without telling you how we're going to keep these charges moving. Because if we don't keep them moving, they're going to stop over here, cancel the electric field, just like everything we've done up to this point. Okay? Fine. So that's that first paragraph of your book. That's the only reason why I did that. Okay, so we're going to try to do this now, but we've got to keep the charges moving. So now we want to define what current is. Current is basically if I have a rod like this, and I've got charges moving through that rod, I've got charges moving through it. Okay, charges moving through it. The current is the amount of charge that moves through a cross section in a given time. That's the definition of current. Current is equal to the amount of charge, Q, that moves through a particular cross section in a given time. Now, in 100, we say this. Delta Q over delta T. Charge it moves through in a given time. What are we doing here?
Not that.
Integrating it.
Well, not integrate, but
Differentiate.
dq dt. We can shrink the time down to 0. Okay? $100 cannot shrink time down to 0. Time down to 0 doesn't make sense to 100 students, at least mathematically. We can tell them you can do it, and we give them a formula that we've derived out of nowhere, but they don't have the mathematical idea of exactly what an infinitesimal time is. Shh, don't say. By the way, he said neither do we. That's what he said. All right, so units of current. We use capital I for current. Capital I is current. Lowercase letter I we also will use for current for time to time. Okay, so what I usually like to do is I like to talk about capital Q and capital I as being kind of a macroscopic view. Little q's, infinitesimal, idea of little q, something that's variable with time. Little I, something that's variable. That's my preference, but it doesn't matter. I, Q, doesn't matter whether it's capital or lowercase. Okay. And the reason why we don't use C is we use C for a big bunch of other stuff. So the reason to use C is we use I. Okay. Now here's something that's fun. Okay. The direction of the current, because it does have direction. It does have direction. Okay? The direction of the current is defined by convention. By convention. The direction of the current is the motion of positive charge. That's by convention. In terms of physics, okay, because charge can have two signs. It can be negative or positive. The physics doesn't change if positive charge is flowing one direction or negative charges are flowing in the opposite direction. The physics of that does not change. Okay? There is an experiment that you can actually do to prove which charges are actually moving, which is kind of cool. But in terms of our circuits, conventional current we assume is being motion of positive charges. However, in reality, in 99% of the cases, there are certain semiconductors which you can create that will actually have effective movement of positive charge. That's the exception. 99%. If I have a metal copper wire, what's moving?
Electrons.
Electrons. Protons aren't moving. Protons are sticking them, But we don't like having a negative sign and then multiplying by another negative sign again. So we just say, forget that. We're just going to pretend that positive charge is what's moving. Okay? And it's good enough for most government work. Okay? Especially the government these days. Oh my. I think we're going to move to Canada. I'm getting scared, to tell you. I mean, I know we've always had bad choices for presidents.
They're having a party for.
Now we're scary.
It's not going to matter. None of them are going to do anything Trump says. None of them are going to do anything Bernie says, and no one likes Hillary.
Hopefully she'll be in jail.
It's like, I'm being honest, none of this next 4 years of presidency is not going to really do an effective
That's
job.
true. That's true. It is sad how little power the president actually has.
Checks and
I
balances.
mean, he tries. Well, it's not checks and balances. It's like, okay, so I'm going to diverge here. Okay? I'm not your official CSUN. This. The things that I say in the next 2 minutes are not the opinions of Cal State Northridge or anything else at Cal State Northridge.
You need to say that for the recording.
Turn that off. No. Destroy all copies of your recording. Have you heard about Justice Scalia? Yeah, Anton Scalia.
Yeah.
Passed away.
Mm-hmm.
Apparently, they can't even appoint a new Supreme Court justice until the next election. Because even if Obama nominates somebody, the Republicans are controlling the Senate, and they have vowed to block any nomination that he makes.
What the Democrats did against Bush at the end of his election, and what the Democrats also did in, the late 70s?
Mid-80s with Judge Bork.
Oh, Bork, yeah.
Okay. But it's like the president it's because the Supreme Court unfortunately has become, apparently, even though the Supreme Court was originally designed to be kind of above the political fray, the Supreme Court these days is just as political as any other. So. All that to say, positive charge is the direction of a motion of positive charge is the motion of charge. Okay. Now, we can look at this on a microscopic level. And so we can look at where we talk about this charge. So if we look at a little diagram here and here, okay, there we go. All right, so we want to look at this in terms of what's going on microscopically, and let me draw a bigger diagram. Okay. So what we want is we want to count the number of charges that pass through this thing in a particular time delta t. In a particular time delta t. So if we look at it microscopically, what happens when you accelerate, when I put an electric field and accelerate my completely hypothetical positive charge that I've put in there, is it's going to accelerate along the electric field until it bumps into something, mainly another atom. Then it's going to bounce off of that atom in some random direction and then begin accelerating along with the electric field. And so what happens is we kind of make an average velocity that turns out of all of this, kind of an overall average of the velocities of the charge carriers that move through this, known as the drift velocity. So they kind of all reach, after all the little bumping around, they kind of all reach a sort of steady state where their average is going to be this drift velocity. So the drift velocity, Vd, that's your drift velocity. So the volume of those charges that pass through here, delta t, this distance is V delta t. Okay, that's the volume basically of charges that pass through. Multiplied by the area of your wire, the area of the wire. And so that's the volume. Now what I want to know is I want to know the number of charges in there and the charge of each one. Since we're just looking at magnitude here, I'm going to say absolute value of Q. Well, unless I have specific ions that I have created, okay, ions that I've created, irregardless, it's either going to be an electron or a proton. The absolute value of that charge is our constant E. Now, the problem is that we can't, there's too much stuff here that depends on that. So we've got current is equal to, that's my Q, that's my charge, divided by delta T. So I can divide out the delta T's. So I've got that my total current in this thing is equal to NQ, I'll just assume it's positive, VD, drift velocity of them, multiplied by the area. Well, that's not going to work. Because once again, I have a couple of things that are ambiguous. Okay? I've got my density of charged particles, I've got my charge of each one, I've got my area, and I've got my V. But they're still ambiguous in terms of the current moving through this wire, and that's the area of the wire itself. So once again, we have to kind of do what we did with that electric field. So instead of looking at current as a whole, when you go to the microscopic level, we need to have a density. Now this variable is used and is used later, which is why I'm introducing it now. So those of you EE people will thank me for this eventually, okay? What we do is we define a current density. Current density J. And that current density is current per unit area. And so on a microscopic level, the current density J is equal to the density of your charge carriers, N, multiplied by the charge of each one, which in this case I'll just say it's E, multiplied by the drift velocity, VD. There you go. And that's looking at current density on a microscopic level. On a microscopic level.
Professor,
Yes.
can you explain VD again?
VD is what we call the drift velocity. In other words, it's kind of the average velocity that those charged particles, charge carriers, end up with after bumping into all the atoms. So in other words, if I just put E in here, it doesn't just keep accelerating. Okay? because there's other things that are going to block it. And so what ends up happening is that it ends up having a constant velocity after all the kind of forces balance out. And so that there's an average velocity that those electrons are going to end up having. Okay? Even though it's really electrons going this way. Now, in the last 5 minutes, I am planning on posting up a team problem for you guys, a group problem for you guys. So I want you to reconnect with your groups because it's been a couple weeks. So use the last 5 minutes to reconnect with your groups and get his number, and then you're dismissed. We're actually a little bit ahead. I got a little bit ahead in the next chapter, so we're fine to do that. So current density. Current density.
What is the rubric? Next class?
Oh, I'm going to put it online, and it'll be due on Monday. When you come back with the capacitor assignments too. On the capacitor assignment.
We have Sunday homework, right?
Yes, there's Sunday homework. Yeah. So we introduced capacitors. Capacitor is a device that stores charge. Its definition of capacitance is it's a charge stored per unit voltage. And the way we're going to be using it from now on is we're actually going to be talking about the potential. So the potential across capacitor is the charge divided by the capacitance C. Okay? The reason why I'm solving this for the electric potential, our definition for the electric potential, is because the other circuit elements that we're going to be looking at, we're going to solve them all in terms of the electric potential across them. So we're going to start with this one here, it's a capacitor. Okay, then we talked about capacitors in series. In series, 1 over the equivalent capacitance is 1 over C1 plus 1 over C2. In series, the charge on the capacitors is going to be the same, and the voltages are going to add. In parallel, the equivalent capacitance is equal to C1 plus C2. In this case, in parallel, the voltages are the same and the charges add. And then one more formula we had last time is the capacitance of a parallel plate capacitor, which is the constant epsilon naught area of the plates divided by the distance between those plates. So those are the formulas that we had. Today we're going to talk about energy. Because if I'm storing some charge, if you store something that can be used again, that can be taken out and used again, that's storing some energy. There's some energy involved in that. And so we want to look at that. Now, if we just take a look at the plates and say that I have a positive Q on this plate and a negative Q on this plate, and I have a voltage across here, V, you might think, well, the energy of a charge placed at a particular voltage is the charge placed multiplied by the voltage V. So you might think that you just take the Q and multiply it by the voltage V. And you wouldn't be that far off. However, that would assume that we're taking the entire charge Q and put it on that plate when the plate is at a voltage V. But that's not the way you charge a capacitor. In reality, what we have to do is we have to take a look at each charge going onto the plates of a capacitor. When the first charge goes onto that plate, there's no voltage across that plate. So when the first charge gets on the plate, there's no voltage. When the second charge comes onto the plate, the voltage is only that of the very first charge. So instead we have to take a look at each little charge as I put it onto the plate, and the voltage that's on that plate when it's there. And so what we do is we say, well, I'm going to put a little charge, and the little charges, anytime we say little charge, that means dq. Okay? And then the charge that's on there is going to be this charge Q, where I'm using Q here as the lowercase to represent the little charge that happens to be on the plates when I add the little dq to it. So then the voltage that the energy that I add is the voltage on the plates at that particular time, which is Q over C, multiplied by my dq. So this is my energy to put each little charge dq on there. So then all we have to do is integrate. We start out with 0 charge on the capacitor, and I end up with capital Q. Okay? The 1 over C is a constant, so I can pull it out. What's the integral of Q to Q?
Q squared over 2.
Q squared over 2. Okay. I put the capital Q in, I get Q squared. I put 0 in, I get 0. So the total energy on a capacitor is Q squared over 2C. I just rewrote this down here because I have no room outside of here. We can now use this formula here to substitute in and put this in terms of the different variables. So there's actually 3 forms of this. There's one where we have charge and capacitance, one where we have capacitance and voltage, and the other where we have voltage and charge. Okay? So if we solve this by substituting in for capacitance here, C equals Q over V, what we get is we get 1/2 Q times V. And notice that that is almost the same as what you'd come up with if you just put the charge and the voltage. Okay? So as I said, you're not that far off, except for because we have to put the little charges on one at a time, you can't just throw the whole charge on there and you know, and it doesn't start out with the voltage V. See, it doesn't work. Okay? So it's 1/2. And the other one is 1/2 CV squared. So depending on which variables you're given, these 3 formulas are interchangeable. What I like to do is I like to memorize one of them, if you're in, memorize one of them, and then solve for the other ones. Which one do you think I like to memorize?
Last one. Middle.
The one in the middle. It's easiest to remember. You know, because I'm just multiplying 2 things together. So. Yes?
So when can you use the first one you wrote, or is it wrong?
All 3 are valid. Oh, the one at the top? This is the voltage.
For you.
This one here?
Yeah.
This is for placing a charge at a voltage that's already there. Okay? But in this case, we're not placing the charge at a voltage that's already there. The charge is kind of making that voltage. So you have to kind of add them up. In other words, if I had this whole thing at V already and threw a Q on there, then yes, QV. But that's not the way capacitor works. All right, now, this energy this energy here can be said to be stored as in the charges. So this is in terms of the charging capacitance. But there's something else going on here, and we're going to use the example of a parallel plate capacitance to derive something that it works in general. Okay? We don't tell you it works in general, but it does. Okay, so we're going to derive this general formula from this very specific case. So in other words, we're going to use the wrong kind of reasoning, which is inductive reasoning. I'm going to do it in this one case and then say it works everywhere, just because we don't really have the mathematics to, in fact, I forgot how to use the mathematics to actually derive it for everywhere. So what we want to do is we want to take a look at the energy stored because there's an electric field here. Because we might not know about the charges. We might not know that this is a capacitor. But anytime I have an electric field, it implies there's charges somewhere. There's charges that have been placed somewhere to create this electric field. And there's a certain amount of energy that was required to put those charges there. And so what we're going to do is we're going to look at the energy just in terms of I have an electric field. If I have an electric field, it implies there's some kind of energy involved in moving charges around to create that electric field. So instead of looking at the energy in terms of the capacitance, we're going to take a look at it in terms of the electric field. So the electric field has E. And if we remember what that E is, in between two plates, I've got one plate with sigma over 2 epsilon naught. The other plate contributes sigma over 2 epsilon naught. So the total electric field in the area in between is sigma over epsilon naught. So that's my electric field in between these plates. Now I want to take a look at the energy that's stored in this capacitor in terms of this electric field and this electric field. Okay, so let's see. So I've got my parallel plate capacitor, and there's area on the plates A, the distance between the plates D. And so I'm going to go back to, let's see, I want to go to this one right here. And the reason why I want to go to this one is because I have my voltage V I can put in terms of the electric field.